Hello, my name is Elijah Potter. I've worked in analytics and data science for about 4 years and will graduate with the Data Science Masters from SMU in December. Over the course of this presentation, we're going to discuss a serious topic, the Ohio opioid epidemic. This subject tackles a nationwide crisis, and the numbers and facts we'll explore soon are undeniably sobering. That said, we won't just focus on the problem. During my time at SMU, I've gained a valuable set of skills, and now we're going to put them to good use. Our aim here is clear. We want to make a positive impact, and we want to help. The US opioid epidemic is a severe public health crisis that has deeply affected communities nationwide. It began in the early 2000s, marked by the widespread misuse of prescription opioids, resulting in a pervasive problem of addiction. To understand the gravity of this crisis visually, we'll refer here to this figure by Visual Capitalist. This illustrates three clear waves of opioid-related deaths that have unfolded over time. During the first 10 years, we saw a sharp increase in deaths linked to pharmaceutical opioids. This rise can be primarily attributed to irresponsible prescription practices that fueled the rapid escalation of the epidemic. Moving into the next decade, we can observe a change in this trend. Heroin, a cheaper and more accessible alternative, started to become the preferred drug of choice. Yet, the most alarming and deadliest phase of this epidemic occurred after 2013 with the emergence of synthetic opioids such as fentanyl. These alternatives are not only cheap, but are also incredibly potent, making them an especially lethal element of this crisis. Another comparison from an OSU study. This reveals a significant rise in US overdose rates, exceeding 19 per 100,000 people. During the study, the yearly overdose deaths surpassed the highest annual deaths from car accidents, AIDS, and gun-related harm. Today, drug overdoses are the top cause of death for Americans under 50. I share these numbers to provide context for this next comparison. During the same time frame, Ohio had almost twice the national average rate. Shifting our attention to the period from 2010 onward, we observe a 60% increase in US overdose rates, and this is dwarfed by a 125% rate increase for Ohio. If we observe increases in death rates in Ohio's 5 largest cities, we witness some astonishing leaps. This epidemic has had a devastating impact on Ohio. Deaths have surged, overwhelming the healthcare system with demand for treatment and recovery services, and communities have been torn apart by addiction. At the crisis midpoint, the cost of care and treatment for those grappling with opioid addiction was estimated to be $28.9 billion. Lost productivity costs for overdose victims were an additional $21.5 billion. This opioid crisis is a complex, massive issue influenced by various factors, including prescription practices, widespread availability of opioids, social and economic factors such as poverty and healthcare access, and the dynamics of Ohio's healthcare system. Given this complexity, a solution must also be comprehensive and multifaceted. Ohio has adopted a multidisciplinary approach to combat this crisis, including improved opioid education, expanded substance abuse treatment programs, changes to law enforcement strategies to reduce distribution, added monitoring services to cut overprescription, and increased funding for long-term recovery in the form of sober living housing. So, what is sober living housing? These are long-term, self-managed communal homes with 5 key traits. They offer a drug-free living space for long-term sobriety seekers. Formal treatment is not required, but it is strongly recommended. There's strict enforcement of house rules such as sobriety, meeting attendance, and home upkeep. Residents are expected to cover their own rent and living costs. And as long as a resident follows these rules, there's no set limit on how long they can stay. And that length of stay is important. While many factors affect long-term recovery in sober housing environments, a well-known predictor of success is how long someone stays in the program. Specifically, if a resident stays at least for 6 months. A 2016 study revealed that about 50% of residents leave within the first few months, often leading to relapse, arrest, and repeat offenses. However, staying for at least 6 months significantly reduces substance use and increases employment rates. Given how disruption affects success, recovery housing organizations are keen to know what factors influence length of stay. One such organization is Ohio Recovery Housing. Founded in 2014, ORH has played a pivotal role in recovery support in Ohio. Earlier this year, I partnered with them in my role as a data scientist at Mighty Crow Media to analyze factors affecting program disruption. Furthermore, our task was to use this analysis to create a risk assessment model to predict the likelihood of disruption when someone enters the program. As part of the prediction, key risk factors associated with the output would be identified to help improve treatment practices. Now, for this model to provide any real value for ORH, it would need to be interpretable, powerful, and usable. So, what does this mean? First, the model's output must be easy for anyone to understand. Second, it needs to be good at spotting disruptions without making many mistakes. And third, it should be user-friendly for non-experts, helping them to make decisions around treatment. It's important to note here that in this situation, making a type 2 error, also called a false negative, is significantly more serious than making a type 1 error. If we wrongly say that a resident might disrupt, it could lead to unnecessary resources spent on their recovery. But if we wrongly say that they will not disrupt, it could increase the chances of relapse, repeat offenses, and even death. To conduct our analysis, we gained access to a dataset of intake and discharge surveys. There were two versions of these surveys, the original, spanning approximately 6 years, and an updated version, which was introduced in May of 2022. The update here aimed to improve upon the shortcomings of the original. These included issues like free-form responses, a lack of detailed questions about demographic information, and the fact that participation in the survey was completely optional. Combining these two surveys presented a myriad of challenges, mainly due to the differences in their structure, particularly the presence of open-ended responses. For instance, in the updated survey, there was a question about education with 7 predefined response options. However, in the original survey, there were more than 140 unique responses to the same question. To simplify the merging process, we employed lasso feature selection on the updated dataset. This helped us to identify the questions that were most relevant to predicting disruptions. We then focus on these questions, collecting, mapping, and encoding survey responses into a feature dataset that could eventually be merged and then used for modeling. Furthermore, since this dataset would be continually expanded for future implementations, we developed a Python module to automate upcoming data cleaning steps for predictive purposes. Now, to kick off our modeling, we started with an unsupervised machine learning technique known as k-means clustering. High-level overview of this, first we decide on a cluster count, then we randomly place these center points within the data, assign data points to the nearest cluster based on their proximity to the centers, and then readjust the centers to find the best fit. Our goal here was twofold. We aimed to identify relationships within the feature set, and we could use cluster assignment as predictive features to help improve model performance. Now let's talk about our first model type, logistic regression. Logistic regression is a widely used method for classification tasks. It's an extension of linear regression, making predictions between 0 and 1 using a sigmoid function. It's popular because it performs very well and it's very easy to understand. To tune our model, we used a randomized grid search method to test hundreds of combinations of parameters to find the best ones. With logistic regression, we aim to find clear connections between survey answers and the chances of disruption. Next up, we fine-tune and build an XGBoost model for predicting disruptions. XGBoost, short for extreme gradient boosting, is known for its strong performance in classification tasks. This method combines a series of decision trees, with each tree working to reduce the errors from the previous one. These XGBoost models are robust and high-performing, making them a great choice for our task here. Finally, we'll train a dense neural network on our survey data. These networks consist of layers of interconnected neurons, where each neuron takes an input, processes it using learned weight and an activation function, and then produces an output. For our task, the structure will include an input layer, several connected hidden layers, and a sigmoid output layer for binary predictions. Neural networks are well known for their high performance and classification. They can uncover intricate and nonlinear relationships within the feature set. However, one drawback is their lack of interpretability, which can pose challenges for our specific use case here. Finally, we would compare our 3 candidate models with a series of performance metrics. We have accuracy, which measures the rate of correct predictions, precision and recall, which help to assess positive prediction accuracy, specificity, which evaluates negative prediction accuracy, and F1 score, which balances precision and recall. Next, we have our macro F1 score, which averages F1 scores across each class. We have negative predictive value, which evaluates negative prediction accuracy We have log loss, which quantifies overall model performance with an ideal value of 0. We have balanced accuracy, which averages recall scores for each class. And we have average precision score, which summarizes the precision recall score. Given the significant impact of type 2 errors here, we're going to prioritize metrics summarizing positive predictions, meaning disruptions, in our final model selection. Great. Now let's discuss some of our key findings. We discovered a strong negative correlation between employment and disruption. Full-time employment or part-time employment was linked to a 28.1% drop in disruption rates when compared to unemployment. This correlation is statistically significant at the alpha equals 0.01 or a 99% confidence level, supported by negligible p-values. Notably, the confidence intervals in our comparison figure show substantial gaps. Other significant correlations include document status, where owning at least one legal document, such as a driver's license or social security card, correlated with a 20.5% drop. A positive mental health score was associated with a 19.6% decrease in disruption risk, while a positive physical health score was linked with a 15.3% disruption. Parents tended to have a 10.8% lower rate of disruption when compared to non-parents, and residents under the age of 40 showed a 7.1% higher disruption rate than when compared to their older counterparts. Now, residents identifying as transgender or non-binary were associated with a 23.3% higher disruption rate, while residents identifying as non-heterosexual had a 21.1% higher disruption rate than their counterparts. Before we continue, 2 important points here. First, we had the option to either split the dataset and control for these differences, or use them as predictors of disruption. Generally, keeping them as predictors improved overall model performance, with the exception of age, which we controlled for. This means that our final model set includes 2 models for both under 40 and over 40 age groups. Second, demographic features like gender identity and sexual orientation were found to be significant, but they were only available in the updated survey data. This means that over 2/3 of these values for the whole dataset were null. As such, they were not included in our model's feature set, but future iterations may consider them. Now, let's explore our cluster analysis results. In our k-means tuning, we found the optimal value to be 4, creating 4 resident groupings. Cluster 1 was compiled of parents with high volunteer involvement and strong health scores. Cluster 2 was dominated by residents with low physical and mental health scores. Cluster 3 consisted of residents with low program usage, less education, higher rates of unemployment, and limited legal documents. And Cluster 4 was characterized by residents actively engaged in recovery program activities, including events, religious outings, support groups, and resident activities. Next, let's take a look at our final models. Our tuned over 40 logistic regression model uses ridge regularization, balancing complexity, and overfitting. The small c value further enhances this regularization to better generalize to new data. Including an intercept here allows the model to account for any survey data bias. Moving on to model performance, and just a note, we're going to walk through the whole process for this model, but we'll skip these steps for the others to save time. The area under the receiving operating characteristic curve measures the relationship between true positives and false positives, which is quantified by the area under the curve. An ideal score here is 1, which indicates perfect discrimination between disruption and non-disruption events. With a value of 0.82, this model shows promising performance. Now, let's take a look at our confusion matrix, which shows us how our model makes predictions. It's clear here that our model favors disruption, but that makes sense given that about 75% of our residents left the program early. Next, we'll dive into how well the model performs. Our model is accurate with over 83% correct predictions. It's quite effective at spotting disruptions, as shown by the high F1 score of 0.902. However, as we saw with the confusion matrix, it seems to favor disruption predictions, as seen in the specificity score of 0.322. Now, let's take a look at how our model interprets our features. This is a list of the statistically significant features in the model. We notice here that employment features have both the highest impact and highest significance. By employing an exponential function on our weights, we can directly see the effect of each feature. For instance, holding all other factors constant, a full-time employment survey response is linked to an 80% reduction in disruption likelihood. It is important to highlight that our model associates a significant increase in disruption risk with attending 12-step programs. Since this runs contrary to an abundance of research in the field, I'd like to emphasize the difference between causation and correlation. For example, 12-step attendance may be linked with other factors such as current drug usage, which is also a key indicator of disruption. Generally, we want to minimize correlation between regression features, but this is not always feasible. Now, for our second logistic regression model for the over 40 dataset, we see that it heavily relies on ridge regularization with a small c-value. We use the stochastic average gradient descent optimization algorithm. This is generally optimized for larger datasets, but it seems to be suited for our needs here. And lastly, including intercept accounts for bias in the data. This model highlights full-time employment and legal document status as significant predictors. Note that while only 3 of the final features were significant, this is not a full list of model features for this. Again, we can apply an exponential function to model weights and see that full-time employment is linked to a 63% reduction in disruption probability when all other factors remain constant. Next, we have our XGBoost models. Our under 40 model employs moderate gamma regularization, a low learning rate, and a maximum depth of 11. We use L1 and L2 regularization to prevent overfitting and balance class weights for non-disruption events. A feature-important analysis reveals that full-time employment is by far the most influential factor in this model. Mental health and document status also have an impact, but employment is key for this. Now for the over 40 XGBoost model. This structure is quite different from the previous one. It uses a higher column sample by tree value of 96%, which captures more of the features in each tree iteration. Furthermore, it utilizes a low learning rate and keeps the tree depth shallow at 2. This helps the model work well with new data. Once again, we apply class weight to non-disruption events to handle the imbalance in our data. Analyzing feature importance, we observe that this model still gives great importance to full-time employment. However, it also emphasizes factors such as mental health, legal documentation, education, and recent alcohol use. And finally, we have our neural networks. The under 40 model consists of a ReLU input layer, 2 sets of ReLU and dropout layers, and a final sigmoid output layer. The rectified linear unit, or ReLU, activation function helps model nonlinear relationships within the data and also helps to ensure scalability. A high initial dropout layer prevents overfitting and improves generalization to new datasets. To understand the relationship between input values and predictions, we use SHAP values. SHAP values help to explain model outputs, assigning a weight to each variable for a given prediction. The higher the impact on prediction, the higher the weight. Our network here favored employment, mental health, legal documentation, and parental status for non-disruption predictions. For disruptions, it relied on 12-step program attendance, involvement with the criminal justice system, recent substance use, cluster association, and positive physical health. It's interesting to note the link here between positive physical health and program disruption. This may stem from correlations between features, or it might be a nonlinear relationship. For now, we're going to take note of this for further analysis. Our second neural network follows a similar structure, but with increased dropout rates and fewer neurons. Much like the over 40 XGBoost model, this approach leans towards generalization and avoids overfitting the data. This model clearly prioritizes employment, legal document ownership, positive physical health, and attendance and recovery activities for non-disruption predictions. For disruptions, it relies on recent substance use, cluster association, limited education, and involvement with the criminal justice system. Interestingly, while the previous model used positive physical health to identify a disruption, this model uses it for the opposite prediction. This may stem from a nonlinear relationship or simply be a difference in correlation between age range and physical health. Finally, let's compare our models. We'll start with our set of under 40. We see here that all models did quite well. Logistic regression was the most accurate and precise, while XGBoost was great at recall. Our neural network was good at avoiding false alarms, and logistic regression found a good balance between precision and recall with the highest F1 score. On a high level, logistic regression was best for spotting disruptions, and the neural network excelled at predicting non-disruption events. Next, we have our over 40 models. Here, the neural network stands out as the top performer, outshining the others in most metrics except for recall, log loss, and average precision score. So this raised a question. Should we choose just a single classifier for our final model? For the over 40 data set, the clear choice would be the neural network, but that would mean losing the interpretive power of logistic regression. Alternatively, we could select for logistic regression, but we would lose on predictive performance. So to address this, we opted for a pseudo-ensemble approach. Since each model in the set performs well and relies on a similar set of features, we would harness the strength of all three. So what does this look like? Here's an example using a recent survey response. This here shows the disruption probability from all three models. For impact interpretation, we rely on logistic regression's decision as our primary outcome. We also have a confidence score indicating agreement among the models. In this case, all agree, showing high confidence this applicant will eventually disrupt. Next, we display survey responses for statistically significant features found by the logistic regression model. You can see survey responses and their impact on disruption. So in this case, imagine that we're running a recovery house and we receive this feedback about a new resident. This resident reported drug use in the last 30 days, which leads to an over 100% increase in disruption probability. Likely, main priority is going to help them maintain sobriety. They mentioned poor mental health, correlating to a 34% increase in disruption. That said, the resident is not in the criminal justice system, which reduces their disruption chances by 51%, which is great. A lack of a driver's license contributes to a higher disruption risk, and a lack of recent alcohol use is a positive sign, as it's strongly related to disruption. Finally, they don't have a job, which is strongly linked to disruption risk. So for this resident, using this information, we can outline initial steps towards long-term recovery. We start by focusing on sobriety. Then we help them to find employment. We provide counseling and mental health services, and we assist in getting their driver's license. Addressing these risk areas directly tackles key disruption factors, which will increase the chance of long-term recovery. Now for some ethical considerations, namely bias. In the challenging role of managing a recovery home, there is a large risk of misusing this model. For instance, imagine that two residents join the program. The first one completes their survey and gets a low disruption score, which indicates that they're likely to stay and recover. In this scenario, one might prioritize this resident to boost their chances of success. On the other hand, the second resident is predicted to disrupt. Given limited resources, someone might invest less in this individual, favoring someone with a higher chance of success. This is not just an ethical concern, but it's crucial to understand that models are not foolproof. The first resident might still disrupt, and the second resident might still defy the odds. Next, I'd like to stress the inherent risks involved with categorizing individuals into historically marginalized groups and linking them to negative outcomes. Earlier, I identified two such groups, and I presented their strong correlation with disruption in bold red lettering because why? A, program disruption, it's a bad thing, and B, red fits in well with my theme. That said, I'm making no claim that simply falling into one of these groups means that you're more likely to fail when it comes to recovery. In fact, following with that red theme, let's take a look at a few other statistics. In a 2022 Ohio study, 25% of transgender survey participants reported food insecurity, and 30% had experienced homelessness at some point in their lives. Furthermore, individuals identifying as homosexual or bisexual were twice as likely to struggle with household expenses and 4 times as likely to experience depression. It stands to reason that factors like these contribute more to disruption risk than personal identity alone. And there we have it. After cleaning and merging our dataset, we introduced 4 k-means cluster features and fine-tuned a total of 6 models. We adopted a pseudo-ensemble approach combining logistic regression, XGBoost, and neural network classifiers to predict disruption events. Using this method, we can predict disruption, emphasize key factors from logistic regression, and calculate a confidence score based on the agreement between the 3 models. We found 5 main themes related to disruption: employment, legal document ownership, alcohol and drug use, involvement with the criminal justice system, and mental and physical health. And most importantly, this model is actually going to be used. Mighty Crow Media, the consulting firm I collaborate with, has secured a contract to build a new data warehousing and reporting solution for Ohio Recovery Housing. As part of this system, the disruption model will be integrated, providing a risk assessment for every new resident. So, starting in summer of 2024, this effort will bring real change to Ohio Recovery Housing, offering hope for recovery to thousands of incoming residents, and hopefully making a difference in the fight against the Ohio opioid epidemic. Thank you.